Greetings and welcome to day 2 of our Climate Adaptation Research Symposium. My name's Michael Jarrett. I'm at the Fielding School of Public Health at UCLA, and it's really a pleasure to welcome you here today to, I think, a really cutting-edge session that's going to have a lot of very sophisticated economic modeling. And I think it's going to be very important to engage in this type of research as we go forward and we begin to really confront the climate crisis and the multifaceted costs that it generates. We often hear opposition to taking action on climate change due to the cost to the economy, but as all of our presenters will show us today, there are a multitude of costs that are generated by the impacts of climate change and our attempts to adapt to it. And I'm really looking forward to hearing their perspectives on total impacts on the economy in Europe. And then we have 2 talks that look particularly at the impacts on agriculture and how interstate trade in one case may mitigate some of the adverse impacts of climate change on agricultural productivity. So I'd like to begin by introducing our speakers today. Our first speaker is Sephie Roth from the London School of Economics. Sefi is, as he just mentioned to me in the prelude to this session, originally from Tel Aviv, Israel, and now lives in London. And he's going to be presenting on, I think it's entitled Some Like It Cold. It's the overall impacts of climate change on European economic output. So I'd like to turn it over now to Sefi and hope that everybody enjoys the session.
Thank you very much, Michael, for the introduction, and thank you very much for the organizing, for inviting me, and also for organizing this really great session and symposium more broadly. So just gonna take the time, make sure that I'm sticking to my allowance. So the paper that I'm gonna present today called Some Like It Cold. And this is a joint paper with 2 co-authors. So I'm just going to make sure that it works. Sorry about that. Yes. Which are Ben Groom, he's a professor of the University of Exeter, a former LSE professor, and Manuel Linsenmeyer, which is a PhD student of mine here at LSE. And I would like to start straight with a bit of motivation to kind of convince that this is a really important topic and why you should care about that. So there is a growing evidence that weather conditions can have significant implication to human health and well-being, and as temperatures are predicted to continue rising over this century, it's important to understand what are the effects of warmer weather on the economy as a whole. To put it in a different way, we want to really think about what are the costs or potentially the benefits from warmer weather. And to do that, one can do it in, very broadly speaking, in 2 different ways. One is to take what I call the bottom-up approach. So we can estimate the impacts of, let's say, daily or yearly level of variation in temperature on something like labor supply, labor productivity, or health. And this is very, very useful. But that's probably not going to give us the total economic cost of changes in weather. So it's very important for us to know how changes in weather affect different segments of the economy or different firms specifically, but we're also interested to see kind of how it affects the economy as a whole. And this group of papers that kind of use this approach tend to overlook that deliberately in order to show something slightly different. Of course, you can kind of aggregate all these kind of different studies together, but that in order to do that properly, one might face some significant challenges, things like overcounting, double counting, and things like that. So it's a slightly complicated task to do. The other approach, again, broadly speaking, is to take a top-down approach. So to look at something like GDP at the national level. And previous econometrics analysis of the global impact of temperature fluctuation on aggregate economic performance, essentially GDP growth, imply that there is a climate economy relationship in which higher temperature are costly to warmer countries, but potentially beneficial to cooler ones. Okay, this is what a few studies that I will mention in a few slides suggest so far. And this is all very good and very, very helpful to know. However, aggregate temperature GDP relationship reflect the net effect of temperature on productivity in all sectors of the economy and across different spatial scales, masking the heterogeneous and local level effects that could inform efficient adaptation policy. And this is a big limitation to this strand of the literature. Why? Because just as economics, stabilization policies are tethered to the vulnerabilities of different sectors or of the economy in anticipation or in response to a recession, policies towards adapting to and decoupling economic activity from climate change should also be informed by the vulnerabilities of specific sectors and specific regions within the economy. So this study used kind of the national account GDP, national GDP, potentially gonna miss this part, which is I think quite important if we want to come up with an efficient and sensible policy. Okay, so in this paper, we're going to try to address that. More specifically, we will examine the effect of temperature fluctuation on growth rate of gross value added, GVA, across different industry and subnational regions in Europe. Okay, we're going to do it across all of Europe. We're going to focus on the heterogeneous response to temperature shock, depending on the local climate and the persistence of these shocks. We're also going to look at spatial spillover effect, heterogeneity across season, and adaptation. But I'm not going to have enough time to show all of the results today. I'm going to show you just some of them, kind of the main results. But all of these results will be available when the paper is going to be out. How are we going to do that? We use a relatively rich socioeconomic and climate data on more than 1,000 small administrative districts in Europe across different industry, and for identification to overcome confounding factors, we exploit year-to-year fluctuation of annual mean temperature within districts across Europe. So essentially, we're going to use within district and sector variation to estimate what we arguably say is a causal effect of weather on GVA. Just to give you a preview of the results, in case I'm going to run out of time or you're going to move to a different session, we find a negative effect of warmer than average years on total economic output in relatively cold district. This is in contrast, this is important, this is in contrast to previous work using global sample of countries which find that cold country productivity increases as annual temperature increases. Famous paper like the paper was published in Nature in 2015 by Burke and others. And this is very important because it's pointing to an overall larger economic cost of climate change in Europe than originally thought. Because if we thought before that in colder countries, actually climate change, warmer weather will be beneficial, we show in our paper that it's actually not the case. At least in Europe, we find that warmer weather in colder countries actually reduce GVA, okay, growth. So this is what, this is kind of the first takeaway of this paper. The second one is that we find that the effect is also persistent, reducing output in several consecutive years after an initial temperature shock. And this persistent effect is also in contrast to other papers. And again, this is very, very important. Why? Well, because it suggests that these shocks also have determinantal effect on the stock of capital or new investment which affect output in future periods, not just in the same period, for example, in the same year. We also find little evidence, if at all, for any effect of higher temperature on total economic output at annual mean temperature above 13 degrees Celsius, again, in contrast to other studies. And very importantly, we examine individual industry group, and we show that the negative effect of higher annual mean temperature on growth rate of total GVA is mainly coming from manufacturing, construction, agriculture, and mining and utility sectors. Okay, so this is what we find in this paper. what I'm going to talk about, what I'm going to do today in this presentation, I'm going to tell you very briefly about the related literature. I'm not going to cover all of it, but just very briefly show you the data, tell you about the data, tell you more about what we do in terms of empirical strategy, and hopefully I'm going to spend most of the time that left for me is to show you some of the results. Okay, it's not going to be a single table in this presentation. It's only going to be maps and figures. So hopefully it's going to be relatively straightforward, and at the end I will conclude. All right. In terms of the related literature, one can kind of divide it into two main groups: the macro level studies that look at national account, look at national GDP. And I already mentioned this paper here, the Burke et al. Paper from 2015 that was published in Nature, very, very influential paper, but other paper that were also published in really good places that suggests, as I said before, that when the weather become warmer, especially in warmer countries, that has a negative effect. But actually, some of these studies suggest that when the climate, when weather becomes slightly warmer in colder places, that actually going to be potentially beneficial. Okay, and this is kind of using the again the top-down approach that I mentioned before. There's also lots of papers that look at the micro level, and this trend of literature documented the impact of daily temperature variation on labor supply, labor productivity, health, and other socioeconomic outcome. Recently, there is also evidence on the effect of temperature on productivity, for example, in China and in India, and there is a really interesting and nice paper that studied the economic output, the effect of weather variation on economic output across several industries in the US, which was published in 2019. There is another paper that is not here actually, and worth mentioning. I'm sorry that I don't have it on the slide. I don't know why it's not here. It's a paper by Tatiana Deriogina from the University of Illinois at Urbana-Champaign and Sol Shang from the University of California in Berkeley. It's an NBR working paper which also look at how variation in weather affect personal income in the US. There is significant differences between the last two papers that I mentioned, that what I'm going to show you today, including obviously it's in different contexts, they study the US and we study Europe, which will turn out to be quite an important factor. So context matter, but also in terms of the sectoral distinction that we'll able to bring to the table, more granular one, the margin of adjustment. Obviously, the results are very different, and also the story of adaptation that we discuss in this paper. All right, so in terms of the data, pretty straightforward. We use data on GVA by industry from Eurostat and the OECD. We have the data at level of NAT3, administrative districts in Europe. The data on temperature and precipitation, we use reanalysis data. Data is based on analysis for relatively common one that people use in the literature from the European Center for Medium Range Weather Forecast, and especially refined using the model Cosmo. I think it's better to, I'm just going to show you the data actually. So this is how the data look like. I promised to just show you map and figure. This is what I'm trying to do here. So on the left-hand side, there is GVA per capita across Europe. And for anyone that knows Europe, that's not going to be surprising at all. You can see that in kind of east and south areas, GVA per capita tend to be slightly lower compared to Central Europe here around Germany, Switzerland, and also where I am right now around London here in the UK. Also, some Scandinavian countries have very, very high GVA per capita levels. And then on the right-hand side here, we have the temperature, again, across Europe. Again, not very surprising. South of Europe, Spain, Italy, Greece, Cyprus, warmer places than Scandinavian countries, and central and north of Europe, mainland Europe. So this is just kind of to show you data. In terms of our empirical strategy, very straightforward. We estimate a fixed effect model with growth rate of gross value added, either total or for specific industry on the left-hand side, and we use polynomial of annual mean temperature as our main treatment. This is what we are interested in, and more formally, you can see the regression equation that we have here on this slide. The first one just look at the contemporaneous same year effect, and the second one look at also a few lags, up to 6 lags Actually, this is what we use here to see whether these effects are that we find are also persistent. We put the kind of the obvious fixed effects. So we put district fixed effect, we put time fixed effect, just to kind of to make sure that we compare like with like, and we account for some national or some macro shocks. We try some other specification as well as robustness, and the results tend to be very, very robust to different specification. And I'm going to show you some of it today. Okay, so let me just move straight to the results now, because it's very, very important. So on the left side, you see two figures here. On the top one is well, everything you see on the left is using national GDP per capita data rather than the GVA per capita at a very, very small geographical level. And what you see at the top, this is just a picture on how this relationship look for the world. And essentially, we're replicating here the paper by Burke et al. That was published in Nature in 2015, and the paper that I mentioned before. And we get very, very similar picture to what they received, what they showed as well. Okay, this kind of inverse U-shaped relationship that I'm sure that many of you are familiar with. When we just do the same thing, again, using national GDP per capita just for Europe, we get a very, very different picture. Essentially the opposite. We get almost a U-shaped relationship. So this is the first kind of thing that we found interesting. What's going on here? Why Europe is so different, and what's the story here? And this is also why I suggested before that context really matter here as well. So that's kind of an important first step. But more importantly, if you look at the right side of this slide, this is when we use the subnational GVA per capita data for Europe. And again, it's obviously not very surprisingly, it's very, very similar to what you saw on the bottom left here. And the estimates show that aggregate GVA growth has an approximately quadratic relationship with temperature, with positive effect on economic growth of very cold, and also some evidence for a very warm annual mean temperature. Okay, and the overall relationship here is constructed for marginal effect, estimated different level of annual mean temperature, whereby different countries provide a support at different ranges of annual mean temperature, and you can see here underneath this figure where the support is coming from, because obviously we don't really see really low temperature in places like Cyprus or Greece. So I think that this picture kind of show you where this relationship or each point in this relationship is estimated from. Okay, so this is something that you might want to remember. Anyway, the bottom line here is that colder regions doing worse when it's get warmer, and this is very different than what we knew before. For ease of interpretation and to illustrate statistical significance, the margin effect of temperature change presented in this figure. So I'm going to have to jump over one. What we see here, we basically plot the slope of the quadratic curve that I showed before, and this is essentially the marginal effect, the derivative of the previous function that I showed you. The figure on the left side show the instantaneous marginal effect based on polynomial models without any lagged independent variable. And the figure on the right here, this figure here, show the instantaneous marginal effect and also the cumulative, the long-term marginal effect, which are just the sum of all the 6 legs that we use. And what do we find? Well, we find that the negative effect of warmer than average years on the economic output is quite significant in cold districts. When I say cold district, is places where annual mean temperature is less than 13 degrees Celsius. And when we look at when longer effects are also taken into account, the negative effects are even more pronounced. This is what you see on here on the right hand side. GVA is actually reducing in several consecutive years after an initial temperature shock. And again, as I said in the beginning of my presentation, this is something very important, very different than what we knew before. Just to kind of put these figures in context, at an annual mean temperature of about 11 degrees Celsius, 1 additional degree lowered the growth rate of GVA in the same year by approximately 0.1 0.37 percentage point and by 1.8 percentage point over 6 years. So we're talking about, not just statistically significant, but also economically significant effect. And this finding that productivity is higher in regions remain in colder regions is, as I said before, is in contrast to what we knew before. I'm just going to go to the previous slide because I also want to show you that. The results I show you so far imply that there is considerable spatial heterogeneity in the response to higher than average temperature in Europe, and this heterogeneity is shown in this map that I show you here. Just you can ignore whatever is on the side, just look at what's the big map in the middle. And what we did here, we combined the estimated relationship between the annual mean temperature and the annual growth rate of GVA per capita with the distribution of annual mean temperature in Europe. And what we can see here, we see a positive marginal effect of higher than average temperature found in most southern Europe, up to a latitude of about 45 degrees north. And further, we've also we found that north mostly, further than that, mostly negative marginal effect, where when we move north of 45 degree level. Okay. This is the other thing that I want to show. I see that Michael is here, so I guess I'm running out of time. Is that correct?
You're almost out of time, Sefi. Thank you.
I'm running out of time. Yeah, so I'm just going to finish here. We're just also going to look at, we also looked at the different sectors, as I mentioned before, and this is the figure. Different sectors are affected by that. Different sectors are affected by that. I already mentioned it in the beginning, and I think that I just reached the conclusion, so I will just stop here and let Michael take it from here. And I'm sorry about being over time.
No, well, thank you. That was really fascinating. I think we've all learned something that was unexpected. So that was much appreciated. I'd now like to introduce Professor Sandy Dall'erba, who is originally from France, but is now at the University of Illinois at Urbana-Champaign. And he's going to talk about the U.S. interstate trade and how that will mitigate the negative impact of climate change on crop profits. So also looking forward to this, preview the slides, and it's another really cutting edge talk with a lot of very interesting economic theory and econometrics. So I'll turn it over to you now, Dr. Dall'erba.
Great, thank you so much, Mike. Thank you very much. And thank you so much to the organizers of this wonderful meeting. So my name is Sandy Dall'erba. I'm a professor at the University of Illinois, Urbana-Champaign. What I'm going to speak about today is working in common with a current PhD student of mine and one who graduated 2 years ago. And as Mike indicated, I'm going to be speaking about the extent to which including trade into climate change studies might provide some new insights into a literature, which is obviously very important. I'm delivering my lecture from home, and everything is powered by solar panel. I'm quite proud of it. And we also were very lucky to get money from USDA for this work. So the motivation, I think, is quite clear in the mind of everybody in this conference. We know that climate change is real. It's coming with an increase in the frequency and intensity of extreme weather events. And the reason why it's such a big deal is because at the same time, the world population is growing. We are looking at currently a population of 9 billion people. We're expecting 11 billion by 2100. So there are some increasing concerns related to food security. We need to address this question carefully as soon as possible. I'm obviously not the first one working on those questions of understanding the marginal effect of weather or climate variables on some outcome, more especially agriculture. But I have a criticism with respect to the way it has been done so far in the literature. The way it is set in many prestigious papers, many of you in this conference are familiar with, is the fact that the marginal effects that are being estimated econometrically pay attention to the extent to which the weather or climate in some location I is going to have an effect beta on your outcome, agriculture, in that same location I. There is quite often absolutely no spillovers. And it seems to me that it's time to think about that more carefully. Based on my experience in this area, it seems to me there are three networks by which spillovers can be accounted for. One is geography, and I have done a bit of work along those lines. But I think also that surface water is another way to look at how places relate with each other. I just published something along those lines. But today I want to speak about trade, and including trade into those econometric estimates. Including trade, and more especially a matrix which is endogenous in econometric setting, is really novel. And unfortunately, the literature, even though it has focused on that particular aspect, has been working with endogenous W matrices which are time invariant. I'm going to show you that we can actually include endogeneity of that W matrix, as well as the fact that it evolves over time. And my general story here is to basically also get a sense of the extent to which trade can act as a mitigating factor to climate change. There has been some studies at the international level, but none at the domestic one. I quite often start this talk by getting a sense of where people stand with respect to their understanding of how much the US import and export agricultural commodities. And I give three choices, and most of the time everybody got it wrong. So to give you a sense, the US is a very self-sufficient country. In other words, only 11% of US agriculture is actually exported to the rest of the world. Inversely, if you take stock of the amount of food that is on the US market, only 8% has been grown in foreign country. So the US is a country which is really self-sufficient. So that's an important element to understand because it justifies why we want to focus on domestic trade within the US. So what I'm going to do in this work is an econometric setting whereby I have two steps to complete. In the first step, I'm going to build a structural gravity model. I'm going to be paying close attention to the extent to which interstate trade in the US is a function of a set of different factors, including drought, which are taking place in an origin state and in a destination state. And the results are going to indicate that exports of a particular state are going to be negatively affected by a local drought, as you can imagine, because yield has decreased. But at the same time, exports are going to be positively affected by a drought which is taking place in a state you are selling to, because their own yield has decreased. Suddenly, they need to import much more from you. And I'm going to use that information, that new W endogenous weight matrix, into what is called an SLX setting of the fairly famous Ricardian model that many of you have already come across. In a traditional Ricardian setting, you will say that a set of local climate or weather conditions are going to affect your output. I'm going to add to that the fact that trade matters very much. Trade will have a clear effect on your agricultural profit. And by in conjunctions, it means that weather events, including drought, in destination places will affect your own agricultural profits. So how do I address those questions? So first of all, I need to rely on some very good data. It turned out that I'm quite lucky that the Bureau of Transportation Statistics here in the US has recently developed that database called FAF, Freight Analysis Framework. I'm going to be using a panel looking at the trade flows across all the continental US states for 4 time periods with a focus on major crops, fruits, and vegetables. In this work, I do not pay attention to livestock or even food manufacturing for the reason that they tend to be slightly less sensitive to drought event, which is really the focus of this study. To give you a sense of where we are in the US with respect to domestic trade, at the very least, one state exports 25% of its ag production, and at the most, one state of exports to other states in the US, up to 89% of its production. Inversely, some states import little and some import more. It goes from 10% to 95%. If I look at this figure here, focusing on the 2 most recent years of my database, I have on the x-axis export, on the y-axis import. You see who the big players are. It turned out my own state here of Illinois is really big in terms of trade within the country. So is Minnesota, California, and Nebraska. We can also look at those trade flows across all the different states, but it's a little bit confusing. Maybe the arrows are a bit small. It's called a core diagram. It gives you a sense of the magnitude, origin, and destination of all those flows. But we can focus on one state in particular. It's going to make my point, which is the state of Nebraska. If you compare the situation in 2007, where the state of Nebraska did not experience any drought, you have a sense of the extent to which Nebraska exported to a set of other US states, and a sense of the extent to which Nebraska imported still those ag commodities from different locations. In 2012, it's a year of a major drought event in the US, and you see that the state of Nebraska was very much affected. What happened? Well, you see that suddenly the ratio of export to import has decreased. The state, being in trouble and experiencing a decrease in yield, will obviously have to rely on other states in order to satisfy the feeding of its livestock or food manufacturing. So as a result, you see that it's a case whereby a state which is experiencing a drought will obviously have experience some consequences on its agriculture, but it will also have an effect on other places which did not necessarily experience a drought, simply because those other places are trade partners of the state of interest in terms of import or in terms of export. I'll focus on drought entirely. There are different ways of defining drought, but we decided to set our mind on one of the most popular measurements. It's called PDSI, the Palmer Drought Severity Index. And we decided to focus entirely on the most extreme cases, so that when cases where PDSI is below the value of -3. Here I give you a sense that those drought events are moving in space, moving in time. The worst year is the final year that I have access to in terms of data, which is 2012. Up to 70% of the US territory was declared under extreme drought on July 31st of 2012. It was really a big deal, more especially for the Midwest where I live right now. So here you have a sense that this drought measurement, which on the first place comes from monthly data at the county level, have to be transformed into measurement at the daily level, at the state, for each of the states, which is my unit of analysis. So we do a bit of a transformation here, weighting basically the county level measurement by the share of cropland and aggregating that to the state level so that I can really get access to the degree of severity of that event, a sense of its geographical location throughout the state, and I will also try different form of drought event. I'm going to look at drought event occurring throughout the year, taking place just over the growing seasons, or taking place 3 months before harvest. The reason why there is a little bit of uncertainty on the exact timing that's appropriate with respect to the relationship between drought and outcome is that no one really knows. I have spoken with some outreach specialists of my department. They also do not really know what is the exact timing of that drought event that will have the maximum impact on your harvest and on your outcome. So I'm going to try all the options. Step number 1, as I said earlier, is that gravity model. So some of you might be quite familiar with it. I'm showing you here the reduced form, where I'm going to be looking at the extent to which export from one state I to another state J at time T is going to be a function of different factors. The first set of factors are dyadic effect. I'm going to account for some home state fixed effect, travel time to go from one state I to another state J, whether two states are border with each other. I'm going to account also for a set of push effects, which are the origin, the amount of agricultural GDP of that exporting state, and a measurement of what is called multilateral resistance term, because states could basically be selling to pretty much any other state in the US. Inversely, I'm also accounting for a set of pull factor, how much demand there is, if you want, of those products. Food manufacturing is by far the category which is the most purchasing this kind of activities. No one eats raw corn. It's impossible. It will really get you sick. So we have to account for food manufacturing as the main factor purchasing those particular commodities. We also have multilateral resistant terms. And then at the bottom here, you have the variable of interest, which is basically degree days in origin and destination, rain in origin and destination, as well as a drought event in origin and destination. And I have a set of fixed effect by climate zones and time fixed effect to account for the usual properties we're familiar with. Here are the climate zones in the US, there are 9 of them. Let's go directly to the results. I'm going to focus on column 3 and 4, which are my gravity model estimated by PPML, as common in trade literature. And we do see that if a drought event is taking place in the origin state, is going to decrease its export, but the effect is not significant. The reason why it is happening is because many states actually are able to store some of their crop, and if they were to experience a drought in a particular year T, they would export less, but they will mostly rely on the reserves they've done from the previous year. So the effect is true, is not significant. On the other hand, if a drought were to happen in your destination state, it will have a positive effect on your own export, as you would expect. We've done tons of robustness checks. We believe we have really covered all the grounds we could think of, looking at the relationship in terms of just one category of commodity, in terms of just volume as opposed to price, adding population, ethanol, biodiesel, you name it. At the end of the day, the results are always the same. We figured out also, when teasing out what was going on in terms of extensive and intensive margins, that for the category O2, which are the big crops minus soybean, we do see that a drought in the origin place is going to reduce the number of trade partners you have, and is going to reduce the value of what you are exporting. For the other elements, the relationship is not necessarily different from 0. So now I have set my first stage. I need to focus on my second stage. In the second stage, I'm going to be using that Ricardian model that you are familiar with, of which basic idea, as you know, is to understand either farmland values or agricultural profits being a function of a set of socioeconomic variables in that location I, and a set of climate characteristics in that location I. And there is quite some literature along those lines already. Now, as I said earlier, the one element that, in my view, is missing from this literature is the fact that your agricultural profit is not only a function of that local demand and local weather characteristics. It's also a function of how much you are going to export to other states that you are trading with, because export, as a basic accounting exercise will tell us, is obviously a very important element that is part of your agricultural profit. So as a result, my stage number 2 is the extent to which ag profit before subsidy is a function of local weather characteristics and socioeconomic characteristics, but is also a function of how much export I'm doing to other states in the country. And we do find, obviously, that total export do have a positive and significant effect on your own agricultural profit. And so does, of course, the density in your own state and some other factors, such as, say, precipitation in your own state. So what I'm trying to convey as an idea is this. Hopefully you understand that we need to be more careful with those marginal effects. Without interstate trade, you're going to say that a drought in your own location will have some marginal effect theta on your own agricultural profit. And a drought in any other location will have absolutely no effect in your ag profit. I'm saying that the story is a little bit more complicated. If you have a drought in your own location, it will obviously reduce your own profit. That's a direct effect. It's still there. But on the top of that, it's going to reduce your profit even further, because now you're not exporting as much as you used to be. On top of that, if a drought is taking place in destination location, it will also affect your own agricultural profit, because those destination places are now in trouble. They are going to import more from you and shall have a positive effect on your own ag profit. I really like this approach because it provides me with a spatial heterogeneity in the actual marginal effect of drought, because each location has its own set of partners. No two states share the exact same places in terms of import and export. So now the marginal effect of drought is much more complicated and is space variant. In addition to that, we really do account for those spillovers. So what does that mean? Here you have a map showing you what will be the effect of one extra drought in any of the states of the US. It will have mostly an effect in Minnesota and in the Midwest. And that effect is taking place through two mechanisms, the local one and the fact that those places will be exporting much less. Inversely, we can look at the marginal effect of one extra week of drought in any of your trade partner. And you see that now it has a positive effect on your own agricultural profit, because your partners are in trouble. So suddenly they need to import much more from you in order to carry on with feeding their livestock and their food manufacturing activities. Okay. So what do we do now? That's the last exercise. Just 2 more slides, Mike, before you cut me. We are doing some projection work, looking at different combination of regional and global climate models over the time period that you see on the top, 2038, 2070. And we do rely on some newly built database for what the future PDSI data might be. And here is really the slide, which is a highlight, if you want, of this entire talk. When we try to understand what is the expected agricultural profit at the national level, if you disregard trade entirely, we're going to find, as many others have found in the literature, that at the national level, the losses will be $11.2 billion. On the other hand, if you do include trade into the story and redo all your calculation to understand what the future ag profit will be, at the national level by that time period is going to be a positive impact, not a negative one anymore, and that is $3.3 billion. So what does that mean? Well, it clearly means, in my view, that trade is a very powerful mitigation mechanism. We evaluate it to be the difference between those two outcomes, which is $14.5 billion. So why do we care about all that story? Well, it seems to me that, oh, sorry, that's the timer telling me that I'm done. We care about it because food security is going to be an issue. Doesn't matter how developed your country is, every single country in the world is going to have to face it. And when I started this work, we still had the Trump administration in the US. And you may remember that month after month, trade linkages that were trade agreements that were based with China or Europe were just going south with that administration. So it seems to me focusing on the US itself made a lot of sense because the country could not anymore pay only attention to international trade linkages. I decided to look at this Ricardian literature more closely over the years and to really include effects of dependence across location through trade, because in my view, this is the best way to model those externalities. And to some extent, we're very much in sync with what is being found at the international level. Some of the work of John Riley or Costino, or even some recent work I'm doing with my colleagues, we do demonstrate that at the international level, yes, international trade is also a mitigating factor, but no one had done it at the domestic level yet. I just did it on a US case. I would love to replicate that for other parts of the world. So contact me if you're interested. And then finally, the paper is already published. If you want access to it, I would be so glad to share it with you. That's it. Thank you so much, Mike.
That was an excellent talk, very interesting. And going back to David Ricardo, you know that trade will have these comparative advantages even under very extreme circumstances. And I think that's an important point that you're making. And I don't know if we have time. I guess maybe what we'll do, just to make sure that everybody gets through their talks, is we'll continue with our third talk, and then we'll have a rejoinder at the end where I think we will have some time to have questions and comments from the audience, but I want to make sure that all of our presenters are given their full time. So next we have Pierre Mérel, who's a professor at the University of California, Davis, and he's going to talk about reckoning climate change damages along the envelope. Another very sophisticated talk, and very much looking forward to what I think we're seeing a pattern here of unexpected results. So maybe we'll see that as well in Dr. Mérel's presentation. So I'll turn it over to you now. Thank you for joining us.
Yeah, thanks, Michael, for the introduction. Actually, I'm not sure the results are going to be that unexpected. It's more of a methodological contribution that, you know, you could view the results as either confirming previous priors or you know, being a nuance on what has been found, but really the contribution is more on the method side. And I hope I don't bore everyone to death. I've tried to make the presentation accessible to non-specialists. So before I start, let me acknowledge my co-authors on this, Matt Gammons at Michigan State, who's a former student from Davis, and Emmanuel Paroissien, who's a French researcher at INRAE in Paris. So this paper belongs to a rich literature, some of which has been acknowledged in the previous presentations already, that started in the 90s, and that seeks to estimate climate damages using historical data. So there are inherent limitations to that exercise because we're using the past to somewhat have a prediction of the future, you know. So our study is not exempt from the criticism that could apply to this whole type of exercise. One of the empirical challenges beyond that in this literature is that agents adapt to climate change. They adapt to the climate they're exposed to. For example, in agriculture, which has been the focus of several studies, people may change their crops, shift the growing season, invest in irrigation, engage in multiple cropping when faced with different climates. And as a result, the impact of climate is conceptually, at least, maybe not empirically, but at least conceptually different from the impact of weather. And that's a big problem, because what we care about, what the desired estimand would be, is to identify the effect of climate inclusive of adaptation. Outcomes of interest could be GDP, land values, agricultural production, agricultural value, etc. A lot of the literature at the sectoral level, or when studying geographically limited areas like the US, assumes that prices are constant. This is kind of an assumption widespread in the literature, so we're ignoring trade. And so the basic question that a lot of this literature seeks to ask could be cast as follows: what would be the impact of climate change on the value of agricultural output, say in the US, this is going to be our application, at current prices after agents have adapted to the new climate? So there's an emerging line of thought that cross-sectional studies, which this literature began with, may be irremediably plagued with omitted variables bias. And so in the recent time, there's been a preference towards panel approaches that use weather fluctuations as opposed to permanent climate differences across locations to identify weather effects. But as the previous slide suggests, the impact of weather is not the same as the impact of climate. And if agents adapt, this is a big problem, because we're not really able to translate a weather effect into a climate impact effect. So in this paper, we investigate conditions under which we may still be able to use panel approaches and rely on large and assumingly exogenous weather variation to still identify a climate impact. So we delineate a framework under which this is an all right thing to do if you want. And then we're going to implement it using agricultural GDP data across US counties. So how is this possible? How can the effect of weather be actually identifying the effect of climate? Well, we're going to rely on a central result in optimization known as the Envelope Theorem. And this idea has been floating around for several years. Where we didn't, invent that, but I think we're the first to formalize it in that paper. And without going too much into the mathematical ins and outs, the essential thing that allows us to use this envelope theorem is that agents take these adaptation actions I was mentioning before with a purpose. They're trying to maximize something. And it's this maximizing behavior that is going to give rise to basically tangency between two curves, a curve that we care about that tells us how output varies when agents are allowed to adapt, and the curve that we don't care so much about, which is what happens when weather changes, but agents cannot adapt in the short run. And that's what we observe. And so this tangency result makes the link between the two. And that's what I've tried to represent here on the graph. So on the horizontal axis, you have one dimension of weather that matters, temperature. I'm using two different letters to make the difference between the weather temperature, which is X, and the climate temperature, which is mu. So if you're at climate mu naught, let's say 18 degrees, when weather changes, your output moves along the blue curve. This is the y hat curves, which depends both on the weather X and where you're at. And if you're in a different climate, you would be moving along a different curve, maybe one of these curves that are depicted in black. But what we care about is going to be the outer envelope of all of these curves, and it's the red curve, it's the long-run response that includes the adaptation. And basically, this tangency result tells us that at mu naught, the slope of the short-run response, so the blue curve, is identical to the slope of the curve we care about, the red curve. And so the marginal climate impact is identical to the marginal weather impact. So we're going to use that result to recover the red curve, but from weather differences and not from climate comparisons. So as I said, we're not the first one to have this idea, and there's already some work that has been done before to kind of delineate when this is an okay thing to do. So we need to have, you know, continuous adaptation effects. Another thing is that in the long run, agents need to maximize the outcome of expected weather. That's when you can directly apply that theorem. And from a behavioral standpoint, this is not really satisfactory. In fact, much of the recent literature instead assumes, as it should, I think, that plausibly agents would maximize the expectation of the outcome they care about instead of maximizing the value of the outcome at the expected weather. So that's maybe it sounds like the same, but it's not. And it's the difference between these what I call this naive program P naught on the right, which is maximizing the value of the outcome Y at the expected weather EX by choosing A. And instead, we may prefer to imagine that people are maximizing the expectation of the outcome conditional on this random weather X by choosing A. And so if indeed agents choose P1, maximize P, solve P1 instead of P naught, then you can't directly apply the envelope theorem. So a lot of the paper is going to show you that you can still get tangency, even under P1, which is a good piece of news in my opinion, but there's no free lunch, so you need additional assumptions for that to happen. And the paper does a good job, I think, at delineating what these conditions are. And I'm not going to go into the proofs or the detail. I'm just going to tell you the gist of the argument is that if you want a tangency result under program P1, you need to assume that the function Y is such that the actions A cannot modify the second order effects of weather. And mathematically, this translates into a structural function Y that has the following form. So it's still quite flexible. You see there's functions of X and functions of A that can be anything you want, but the interaction between the two is restricted to be linear in X. So in the rest of the talk, and after we've proven this in the paper, what we do is we assume that this is the case, so that either we're under P naught or more realistically, we're under P1 with this additional structural condition. And then we're gonna basically take stock of the consequences of this. Sorry, I lost the... I'm gonna have to scroll again. Apologize. We're going to take the consequences of this tangency local tangency result to recover this red long run function, basically. All right. So as I said earlier, the tangency result is local. So it's not like the blue curve is equal to the red curve. It's just that they're tangent at mu naught. So what we're going to need to do is get not one, but a collection or a family of slopes along the climate distribution, and then integrate those slopes between 2 points, let's say the initial climate mu naught and a counterfactual climate mu1, for example, like a higher temperature. And this is what is represented in this graph. So we have climate intervals. We're going to estimate slopes at each value of climate using weather fluctuations. And then in a flexible way, we're going to arrange these slopes along one another to recover the counterfactual change delta y hat in the outcome. And one of the beauties of this approach, which was first suggested in a seminal paper by Solomon Xiong in 2016, I think in the Annual Review of Resource Economics, is that it's model 3. So we're going to estimate slope, and then we're just arranging them without imposing any functional form on the long run response. And so what we're going to get is a very flexible response that nonetheless you're going to see is more or less conforming to prior expectations with some important nuances. So our illustration uses agricultural GDP across US county. I think we're the first ones to actually leverage that data set. One of the disadvantages of that data set is that it's kind of short on the time series side, so it's only available from 2001. So we have 17 years of data. As prior studies have done, we're focusing on non-irrigated counties, so counties east of the 100th meridian. We have about 1,300 counties, and our weather data comes from prison. And we think that this is relevant because agriculture is, highly reliant on weather and therefore climate, and there's still debate in the literature, even within the US, on what the impacts of climate change will be once accounting for adaptation. So I've cited some of the more prominent published studies here on this slide. So you may think that it's going to be difficult to estimate a collection of slopes, but we do that within a single framework. So we see you see 3 equations here, but it's just 3 variants of the same one. It's just one panel that's going to estimate multiple slopes at once. And here the notation is quite standard. So we're going to have the outcome y, it's going to be AgGDP or the log of that as the dependent variable, and it's I denotes the county, T the year. It's a 2-way fixed effect model. We include state level trends, which is also sort of the minimum that you do in this type of studies. But then really the coefficients of interest are going to be this collection of beta that are indexed by the climate mu. And that tell you what the marginal response to weather is going to be at climate mu. So we assign each county I to a different climate interval. This is why mu depends on I, and we estimate again a collection of these beta coefficients. In model 2, we make things a little bit more sophisticated. We recognize that climate may have changed, even though the period of investigation is quite short. And so we allow counties to move from one climate interval to another. This is why the mu is now indexed by not only the county, but also the year that you're considering. And then in model 3, this is the most demanding model, and it's kind of meant to show you what you get if you really push the model far. And actually, we're going to see we lose a lot of statistical significance here. We explore other specifications in the paper that I don't have time to talk about, but if you're interested, I really invite you to look at it. And so it's what this model 3 does is basically add additional controls, which are state-specific weather slopes. So we're removing any variation across counties located in different states. The only useful variation now to identify this collection of slopes is going to be variation across counties within the same state, and also variation between a county and itself across different points in time, as counties are allowed to change climate over time. So we're reducing the useful variation, and you're going to see it's going to have important effects on our ability to identify effects. So, so far I've been talking just about temperature, but really we have 2 variables, average temperature and cumulative precipitation measured over the month from April to October. The climate at any point in time is defined as the 30-year moving average. And then for model 1, which assigns counties to climates for once and for all during the period, we just take the simple average of these yearly climates across the 17 years. And we divide the range of climates into 100 bins. So we have 100 bins for temperature and 100 bins for precipitation. So this is what the distribution of the bins look like in model 1, where again, counties are assigned to a climate interval once and for all. In the other models, we would have maps like this for each year in the sample. And so you see, for example, for temperature that you have a clear north-south gradient. So here are the results. And you see, so I'm going to talk only about the effect of temperature because I think I don't have that much time left. So that's the top row. You can ignore the bottom row for now. And there's 4, not 3 panels, because we also compare our results to a benchmark, which is the very first column here, which is a standard quadratic in temperature. So parametric approach. So the first thing to note is that despite the demands put on our data, because we estimate 100 slopes with a panel that is not that long, relative to the parametric benchmark, we don't lose a lot of statistical significance. Actually, we gain some, except for model 3, which, as I said earlier, is going to be extremely demanding on the useful variation. So that's the first thing to note. The second thing is that overall we get curves that are relatively smooth. I mean, you can see in model 2 there's some wiggle along the way, but the overall shape is not completely erratic, and it conforms with basic expectations. Compared to the parametric approach, you see that you have different changes in convexity, which obviously would not be captured with the quadratic, could perhaps be captured with higher order polynomials, something we maybe should show as well. And another thing to note is you don't see much difference between model 2 and 3. So allowing counties to move from one climate to another over time has the smoothing effect, as you would expect, but it doesn't change the overall lesson. Finally, what you see is that if you start from, let's say, the median climate, which is the point with no standard errors here, and you warm, then you see you have a significant decrease in AgGDP. If you look at the scale, it's, if you go from the median to one of the highest points down that curve, you lose about 50%, so it's huge. Obviously, I mean, that's a very extreme warming. If you cool down, you improve, but the effect is not statistically significant, at least not using the more conservative standard errors that we show here, which are state clustered standard errors. And again, for model 3, nothing really significant. It's very, very noisy, although the overall shape is somewhat preserved. So we can translate these long-run response curves into counterfactual impacts. In fact, that's the whole purpose of the exercise. So that's what I'm showing you in this slide here. For the benchmark model, for model 1, 2, and 3. So in the benchmark model, the impact is marginal impact is going to be linear because of the quadratic assumption. And also as a result of this kind of structure we put on the model, it is the case that it's the warmest counties that are affected the most, and significantly so. This is no longer true with the flexible envelope approach. Here you see that it's counties that are in the middle of the climate distribution that suffer the most, and that at the ends the effect is 0 or even positive and not statistically significant. And that's true both in model 1 and model 2. In model 3, you see you still have this kind of like non-monotonicity, but on top of that, you have curves or points that are located on what seems to be parallel curves. And what these curves are showing you are, it's counties that are located in the same state, because if you remember, we are adding state-specific slopes. So if you're in a given state, you have your own state-level slope, which shifts the responses up and down. In terms of aggregate effects, the benchmark panel gives a net effect of -8%, which is statistically significant, and again driven by these hotter counties. In the envelope approach, at least for model 1 and model 2, we get a slightly larger effect of 10%, which is also statistically significant, but the distribution again across counties is different. The effect is driven by counties located in the middle of the distribution, not the very hot counties. And then for the model with state slopes, the effect is somewhat muted. It's 5%, and it's not statistically significant at conventional levels. So the take-home messages of our paper are that we can delineate behavioral frameworks under which marginal weather effects can identify marginal climate effects. These are quite restrictive. If we're willing to make the assumption that agents follow either P1 with the structural restriction we highlighted, or P0, then we can rely on the envelope theorem, but it still only provides a local result, which means that we need to integrate these slopes across the counterfactual range of climates in order to recover the long-run response curve. And our application suggests ignoring model 3, which is extremely demanding, a 10% drop under a 2 warming scenario. So with that, I'll thank you for your attention, and I look forward to the questions. And I'm done. The remaining slides are bibliography slides, so I don't need to talk.
Okay, well, thank you so much, Dr. Mérel. Yeah, very interesting talk. And I think, one of the take-homes from this session is that at least the economic impacts, particularly on agriculture, but also throughout the economy, they're much more nuanced than we might expect. And we can't necessarily say that, warmer is going to be worse in all locations. So let me see what we have in the chat box and try to summarize that for you.
Mike,
someone wants to comment that the idea of the envelope theorem, which aggregates all the different activities, is certainly of interest. The discussion sure tested my knowledge of calculus and economics.
Mike, are you allowing us to ask questions to our to the other presenters? Or?
Yes, absolutely. I just want to see what our audience has said.
Okay.
And we don't have too many. Okay. Yeah, so someone's talking about this August 2020 derecho in Iowa, which has been identified as the most costly severe thunderstorm in U.S. history. It destroyed 10 million acres of corn in the middle of growing season. So if this loss amounts of agricultural product was compensated for by the use of corn product from another state, does that not mean that without the derecho, the U.S. economy would have a surplus of 10 million acres of corn output? How much does your research question address price changes?
Okay, yes, that's a very good point. So the link of changes in prices is a little bit tricky to get, because if the drought or extreme rainfall event, which is the one I think that person is interested in, is fairly local, then it should not really have much of an impact on the price of those crops, fruits, and vegetables. If, on the other hand, we are looking at a massive event like the drought of 2012, it's true that the prices will be affected by that. So to some extent, so changes in prices are accounted for through the time fixed effects that we have in our work. But it might require just a little bit more investigation, because that price effect is a little bit tricky to grasp. So I think the participant here has an interesting question. I'm not totally able to answer it fully today, because that price was not the focus of our work. It's indeed something to investigate a bit more. That's true.
Yeah, just maybe a follow on that theme and ask about how much your models are able to address these extreme events, which seem to they're becoming much more frequent, more severe.
Yeah.
How do they address that? And when we look at, say, for example, bigger impacts in cooler places in Europe, is that explicitly accounting for these extreme events, or is that just looking at the long-term averages? And maybe if you haven't accounted for extreme events, could you speculate on how that might change your results?
Oh, okay. So yeah, the focus was definitely on drought, which is just one of possible extreme events. So we did include it in pretty much any of the regressions we did. The point you're making here, Mike, is figuring out, the extent to which marginal effects of other events, the basic drought days or precipitation, are affected by the presence of a drought. We did not try that. We did not. It's something to think of. It's actually linked to a point I wanted to ask to Sefi, which is whether there is some interest into adding extreme weather events to the work that is done, because it does rely on precip and temperature, but maybe extremes might matter too. What do you think, Sefi?
Yes, I was about to comment as well. So in a way, it's kind of related to the weather not equal climate comment that Pierre made. Yeah, so what I showed in today is more kind of looking at how not specifically looking at extreme weather events, but in the paper actually we do look at that using slightly different methodology, more similar to what I would argue Sol Shang and Tatiana Deryogina used to look at, for example, how one day of a very extreme temperature affect the economy. So we do that as well. Using that kind of model, also going back to Pierre presentation, allow us to kind of estimate directly how people adapt to changes in weather, in the sense that we see whether places were subject to more days of more extreme days, whether they behave differently and whether they respond differently to a shock as well. And we find that it depends on what, as always in economics, it depends. So I didn't have time to show all of that, but I think this is really, really important. So it's important to look at kind of like yearly averages, but also look at extreme events in specific days or in specific seasons. And we try to unpack all of that in the paper, but unfortunately, due to time limitation, I didn't have much time to discuss. And I just want to add another comment, Mike, if that's okay. To the point that Pierre made, which I totally agree that weather is not equal climate, completely on board on this. But I think that when we said that, I think that, when we talk about climate change, we do, we do think that, I think that's a consensus, that it will change the weather distribution and it will change the way that we experience weather. And this is kind of the connection that we need to remember. And this is why looking at weather variation is actually very important. Of course, we need to look at adaptation. I totally agree with that. But I just wanted to make this comment as well.
Yeah, and I just had another question, Sefi, for you, and that is, to what extent in the economics literature are people taking into account deviations from the norm? So that's exactly effects literature that's critical. That you may have heat waves that occur at times of the year where people aren't accustomed to it, and typically you observe larger dose responses at that time. Say, Central California, coastal areas, they experience, and we look at it nationally, Canada experiences some of the worst effects of heat waves if they occur at times where people are not adapted or used to experiencing that. So I wondered where your literature is going in that direction.
Yeah, so two things. That's a great question. So I think, if I understood it correctly, so one, we don't compare, for example, Southern California to other parts of California. We look at within Southern California variation, actually more than that. So we look at the deviation from long-term means in the way that we estimate our equation. So this is, I think, something that it's important to remember. So this is where the variation is coming from, actually. So this is what we do. And I think also related to this point is, again, is the point of adaptation, and whether people react or change their response, whether this shock, which is variation from the mean, happen more frequently. And I think that I agree with what's said before. We need to do more on that. We try to estimate it directly in our paper, but I think that listening to Pierre's presentation today definitely gave me some food for thought. So thank you for that.
And then we have a question from Pierre to Sandy, and I'll let Pierre give voice to that.
Oh yeah, and I also have one for Sefi later. I don't want to take all the space, so if there's people in the audience that are asking questions, maybe we should start with them, and if there's room, I can.
So I do have a few more, but not a lot. So you could go ahead with that question.
Okay. Yeah, Sandy. So your estimating equations use, I assume, the value of exports. So it seems like there's a price effect in there. So how much of your kind of positive effect on profit rely on prices going up when supply is going down, and if it does rely on that, what can we say about consumers? Because then this is a study about profit, but not really about the social value of agricultural production if you're not including consumers in this kind of welfare measure.
Okay, so consumers are still accounted for in that step number 2. You're familiar with the Ricardian model. So at the bare minimum, you include the density of the population, assuming that final consumers will at some point be consuming your product. So it's there. And in stage number 1 and 2, we do have that fixed effect by year. So price variation, in my view, is already accounted for. It's absorbed basically by that. Now, it's entirely based on the idea that the changes in prices will be uniform across the US. That's eventually a point that could be challenged, because it's true that even within a specific year, whether there's drought or not, the price per bushel of, say, corn varies a little bit from one state to the next because of differences, slight differences in quality or geographical proximity to the final users. But I think it's still quite minimal. So I feel quite comfortable with what's presented here because of that, the presence of that time fixed effect.
Thank you.
We just have one comment here, and I think it's from Bob Goldhammer. And he says he's a professional emergency manager with a BS in business management and master's in geosciences, but he still has challenges understanding and explaining this concern about the economic impacts to others. He said, no wonder the general public has trouble understanding it. We need to band together to learn more about each other's areas of expertise to better educate the public, to affect positive growth and the concern for climate change. So I think that's a very good comment, and that's certainly one of the hopes of this symposium, is to bring together globally recognized experts and emerging scholars to address the interdisciplinarity of this field. But it is, I think, another area where thinking about how to translate this to policymakers and the public is very important. And I wonder if all of you could comment on your experience in trying to convey these fairly complex and elegant economics models to a lay audience or to policymakers.
Well, it seems to me that the process we're looking at here is one that is quite common for any field of science. Were you to listen to atmospheric scientists, they also debate for long hours about the right process to downscale the data from their global climate model. So what we see happening today and yesterday among economists, in my view, it's a necessary discussion. I think overall we agree about the urgency of working on those questions. And we have to be, we are basically trained, and our goal is to really provide the most accurate set of results, accounting for different aspects of a very complicated story. So maybe in the eye of someone who's not trained, we may look like we disagree with each other, but in reality, I think there is a high degree of agreement among climate economists on those big questions. Yet each of us is willing to be paying much more closely attention to some specific aspect of that big picture. So the discussion is absolutely necessary to get going with this important question. Sefi, Pierre, what do you think?
Yeah, I mean, I'm kind of new in this literature, but despite that, I've been approached by policymakers. So, and I'm working more on methodological aspects, which you would think are kind of like things that are less accessible. So my sense is that there is a tension. I can't speak about the general public, but at least from policymakers in the US on even these technical aspects, because they inform us on how to interpret existing empirical estimates, and people care about that. So I've had a pretty positive experience in how to extend some of my research to at least to policymakers, and again, this is new and very technical. So I think it would be, I assume it would be the same for studies that are maybe on broader topics, like not focusing only on ag and more empirical than my own work.
Yeah, I mean, if we were to summarize some of the major points that came out of all your talks, one would be that there's still going to be negative impacts, regardless of how we adjust, and that seems, but that there is the possibility of minimizing some of those impacts and adapting to them. Is that a fair statement?
Yeah.
Because those are the sort of bottom lines that, people, because there has been debate in the agricultural literature in cold places that it is going to increase output and increase the benefits. In my home country of Canada, there have been several studies that have suggested that. I don't necessarily agree with them.
Yeah, Michael, I think this is correct. For my paper, we don't really in that paper compare short run and long run, so we can't formally say anything about the process of adaptation or whether there is adaptation actually. Mm-hmm. But I've done that in another paper where that also uses US ag data, and we do show that there is adaptation going on, and we also have evidence from wheat production in France. So yes, I would agree with your assessment, but not based on today's presentation of mine.
Okay, thank you. Let's see, I just want to see if we have another question for Sefi. Does your study and the 2015 study that contradicts the results of yours look at similar areas, locations? If not, were there other similarities between the places that of the two studies aside from cold temperature?
Yeah, so we, as I showed in the beginning of the results section, we essentially replicated 2015 paper, and we found exactly the same thing. So there are 2015 paper, according to our analysis. I mean, obviously we use slightly different data using slightly different time frame hold, and everything is kosher with that. So we have no problem with that. What we show that because what they do it kind of across the globe. They use national GDP level. We use something different. So we just focus on Europe, and we both use, in some point we use the national GDP, but most of our analysis is based on kind of regional GVA. And what we find when we do that, then we find different results. But when we replicate their results, we find exactly the same thing. So Marshall, Burke, and the other co-author of this paper can sleep quietly. Everything is fine with their analysis. But this is quite important because the setting here really matters. So what they found in other places, and the other paper that Sol Shang and Tatiana Deragina has as well, that we just find very, very different results because in different contexts. I mean, this is one of the explanations here. So I think it's kind of it's important to remember that. And I saw that Pierre kind of also asked about that, about the differences between my paper, our paper, and the paper by Marshall, Burke, and others. So the difference is obviously the setting, as I said just now, but we also do many other things. So as I said before, they look at the national level, we look at subnational regions. And also we look at different sectors of the economy. And both of these things are very, very important because we think that, yeah, maybe there is, as I think Sandy kind of suggested, there is kind of interconnection between different regions and different sectors, etc. But that will mask what's going on at, for example, local places, which are very, very important, and also in specific sectors. And if you want to think about policy, going back to Mike's points about how we want to deal with that, we really need to think about the areas that are going to suffer most from climate change, and also about its regions, right? Because they can kind of disappear in the macro, but there's still people, still industry, and we need to think about policies that can help these regions and these sectors to deal with what we think will be a very costly adaptation process. So this is.
I wondered when I saw your results if there was some implicit adaptation that was going on in Southern Europe, where it's typically much hotter than in the Scandinavian countries, where the impacts were predicted to be larger.
No, yeah, so that's a good question. But if you remember in the figure that I show, I said that different part of this figure is coming from different parts of Europe, because you don't really see this really cold weather in Greece or in Cyprus or in Spain. You don't get temperature near zero, to the best of my knowledge. I mean, depends where you are in Italy or something. But this is probably the story. It's not coming from there. It's coming from different places in Europe. So this is what kind of we've been very transparent about where the variation is coming from regionally. But yeah, this is kind of what we are still working on, about what are the actual mechanism and why some places and some industries adapt better than others. And this is something that we're still working on.
Great. So we have a comment from Mr. Goldhammer that he's the IAEM liaison to the National Weather Service Weather Ready Nation and to the World Meteorological Association Weather Ready Nations. And he would like to continue discussions with all of you if you're interested. So he's put his email in the chat box. And I guess we just have a few more minutes. So maybe in wrapping up, in a minute and a half, could you summarize what you see are the most important future research directions in your field?
Well, if I may start, I think the common link between the three presentations today is that we need to be thinking more closely about place-tailored mitigation strategies. I think that Sefi's approach for each sector, each location is quite clear. What's going to happen in place I is quite different from what's happening in place J. Pierre has done fantastic work by providing those marginal effects, which are very local, county level, as opposed to state average. And my work shows that each state has its own set of trade partners. Therefore, what's going to happen for that location is completely different from what is expected from the location nearby. So I think we're going in a direction of place-tailored measurements and place-tailored adaptation policies. That's my view on that. Pierre, so Sefi, what do you think?
Yeah, I can agree on that. I just couldn't help but kind of bouncing back on the previous discussion about the contrast between what's happening in Europe and the global study. I mean, to me, it's a little puzzling. I mean, if things are so different in Europe than they are at the global scale, to me, it raises the question of whether we are even entitled to estimate these global functions, because the underlying assumption is that there is something common across countries, and we can put them on this global long-run curve, and they all belong to there are things that are done, I don't know, in West Africa that can be done elsewhere, but then we have this study that focuses on Europe, and the relationship is completely reversed. So is there really enough commonality across countries to even have the legitimacy to put them in the same regression? That's kind of, and that's something I've been worried about before. My work is not exempt. You could say the same thing and say, well, maybe Iowa has nothing to do with Kansas, so why do you put them in the same regression? But Sefi, if you could say something to that, I would really.
Yeah, I mean, this is part of the reason why we did this study, actually, because I had the same concern about you. I mean, I don't know how you can compare something, a heat wave. If you think about weather shocks that Michael was mentioning before, or warmer than average year of weather, I can't see how we can compare what happened in France to what happened in, I don't know, Bangladesh. It's just completely different setting. There is different kind of institution and many other things. And this is exactly what a study kind of tried to say, going back to Sandy's point. We argue even more than that, even within Europe. I mean, Southern Europe is really different than Northern Europe, and I think there is a lot of story about specialization. So, going back to some of the other comments, I think what's going on behind the scene here. I mean, regions specialize in certain things, and when you have a shock, when you have a deviation from the mean, that really kind of put them off their kind of norm and kind of comfort zone, and that's very painful economically. This is what we see. And therefore, if we think about, different regions, how they affected, and they have different specialization, I think that putting everyone together in the same kind of box, that's something that we don't want to do. So kind of going back to Sandy's point, I think this is kind of the future in this field.
Yeah, okay, well, I think that's a good note to end it on. We're just at time now. I want to thank all our presenters for very intellectually stimulating and I think important talks, and I wish them well as they continue in their research paths. And as a geographer by training, I'm happy to see that people are recognizing place-based approaches. And I know that that's been an important theme in economics too. I'm just making a
Thank you, Mike.
Yeah, so thank you. And we have 3 very interesting sessions upcoming at 10:15. So I invite people to stay around for the end of the symposium. And I thank all of our audience for your participation as well. And thank our technical staff that have made this run smoothly.
Thank you all. Bye.
Thank you very much.